We present attention-based point cloud edge sampling. Deep learning techniques have significantly advanced the development of artificial intelligence, transforming the world. There are many studies have been conducted to unravel the features learned by neural networks from images. These studies show that in addition to color and texture information, shape, silhouette, and edges are also of crucial importance for neural networks. However, for 3D point clouds, there is usually no texture information due to its sparsity. Color information is also sometimes not available. In these cases, shape edges are key features that neural networks should learn. The work of Engel et al. Proposes a model that learns patches for better downstream performances. From the visualization of the patches that learned by the network, we can observe that most key patches are around the shape edges. Hence, we have an assumption: when point clouds are sampled in the middle of a neural network model, would sampling edge points be a better choice for downstream tasks? The existing point cloud sampling methods can be broadly grouped into two categories. The first category is mathematical statistics-based, which includes random sampling, voxel-based grid sampling, farthest point sampling, etc. These methods mainly select points directly based on predefined mathematical rules. The other category is neural network learning-based, which includes SNet, SampleNet, DANet, MOPSNet, etc. These methods train specific neural network models in a task-oriented manner. Instead of selecting points, they mainly generate new points, which are then subjected to various post-processing operations. In this paper, we propose a novel method to sample edge points of the input point clouds. It combines both neural network task-oriented learning and mathematical statistics-based direct point selecting. Our method is inspired by the famous canny edge detection algorithm for 2D images. The key to canny edge detection is to determine the edge pixels with the help of their intensity gradients. We make the following observation: if there are large differences between the pixels from a local patch set, Si, then the standard deviation, sigma I, of the intensities in the patch is also high. Hence, an alternative method for edge detection is to select pixels whose patch sets have larger standard deviations. We further generalize beyond pixel intensities to any per-pixel features with a measure of feature correlation, H, defined between the center pixel and its neighbor pixel. A normalized correlation map, Mi, can be computed between the center pixel and its neighbors for all points. Then the standard deviation, sigma I, is computed over the elements of each normalized correlation map, and pixels with larger standard deviations are selected as edge pixels. Now we transfer the above idea to point clouds and propose our attention-based point cloud edge sampling method. We term it APES. The attention mechanism is an ideal option to serve as the measure of correlation between point features. For local-based APES, we use the local patch attention map as the normalized correlation map directly. To be specific, here we use the latent features of the center point as the query input, and the feature difference between the neighbor point and the center point as the key input. After normalized correlation maps are obtained for each point, again, the standard deviation is computed for each of them. Then the edge points are sampled by selecting the points with larger standard deviations. Now we propose another variant of global-based APES. Considering the special case where all points are included in the local patch, a new global correlation map of size n by n is obtained with the linear layers q and k being shared for all points. Now the neighbor-to-point cross-attention simplifies into the common self-attention. Consider the global correlation map column-wise. For a certain point, in order to qualify it as an edge point, it needs to rank a higher value of normalized correlation value with regard to other points in the global correlation map more often, compared to other points. Hence in global-based APES, instead of computing row-wise standard deviations, we compute column-wise sums. And we then sample the points with higher sum values. Overall, if a point contributes more in the self-attention correlation map, it is more likely to be an important point. We evaluate our method on two common benchmarks: ModelNet 40 classification and ShapeNet part segmentation. Designed neural network architectures are presented here. One thing worth mentioning is how gradient backpropagation is enabled. As illustrated here, the gradient follows the red line, while the orange block of indexing points is purely mathematical statistics-based. It contains no learnable parameters and thus does not need to be differentiable. Now we present our experimental results. In the ModelNet 40 classification benchmark, our proposed APES is among the best performing methods. From the visualization, we can observe that both local-based APES and global-based APES achieve good edge sampling results. On the other hand, local-based APES focuses more strictly on edge points, while global-based APES ignores some edge points and leverages a bit more on other non-edge points that are close to the edges. For example, in chair shapes, global-based APES discards some chair leg points and selects more points for chair seat edges to make the edges thicker. We contributed slightly better quantitative results to this. In the ShapeNet part segmentation benchmark, our method achieves decent performance but is not on par with the best ones. However, as we compute the same metrics on the intermediate downsampled point clouds, we surprisingly find that their performances are extremely good, even far better than the state-of-the-art methods. This indicates the downsampled edge points contribute more to the performance, while the features of the discarded non-edge points are hard to retrieve by the upsample layers. This is due to our method focuses on edge points and the sampled result has a quite different data distribution than the original point cloud. We also have performed many ablation studies regarding the design choices of neural network architectures, including using different feature learning layers, using different embedding dimensions, and using different number of neighbors in local-based APES. A study of comparing successive sampling with direct sampling has also been conducted. We additionally compare our sampling method to previous work including RS, FPS, and the more recent learning-based SNet, SampleNet, LiTN, etc. The task here is the ModelNet 40 classification, and the task network is PointNet. We observe that both local-based and global-based APES achieve good classification results with the task network under different sampling ratios. On the other hand, although other learning-based methods achieve decent numerical results, it is difficult to identify their sampling patterns from the visualization results. Their results look quite similar to random sampling. Our proposed method shows a comprehensive sampling pattern of sampling point cloud outlines. To conclude, we propose an attention-based point cloud edge sampling method that combines neural network-based learning and mathematical statistics-based direct point selecting. Two variations of local-based APES and global-based APES are proposed based on two different attention modes. Qualitative and quantitative results show that our method successfully extracts edge points and achieves excellent performance on common point cloud benchmark tasks. Future work may focus on adding new losses, or designing a new upsampling layer to overcome the problem of data distribution bias. Thanks for watching.